Okay, good morning. Is this slide visible? Anyone,
Yes,
please
sir.
respond.
Yes, sir.
Hello, am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir. It is. You are audible.
Okay, so let's today's discuss another black box testing technique. Maybe we'll try to cover two. One is state table based testing, another is decision table based testing. So that tables are very much useful tools. Okay, tables are very much useful tools for reprinting and documenting many types of information relating to test case design. These tables are beneficial for applications which can be described using state transition diagrams and state tables. I hope you must have studied finite state machines in automata theory also. So similarly here, the state transition diagrams from we can construct a state transition diagram for a given problem. Then we can construct the state table from the state transition diagram, and from the state tables we can generate the test cases. Now let's say before going to the test case generation process using state tables, we'll discuss some of the basic terms. So first term we'll discuss FSM. You have already known FSM, so I will not discuss this thing. We will just simply skip it. You know that FSM is a behavioral model. It represents the behavioral aspects of a system. So it is a behavioral model whose outcome it depends upon both the previous input as well as the current input. So this finite state machine, this model, it can be prepared for software for reprinting the software structure or the software behavior. It can also be used as a tool for functional testing. Okay, and we know in black box testing we test the functional aspects. So this FSM can be used as a tool for functional testing. Then comes next term we'll discuss about state transition diagram or state graph. So a system or its components may have a number of states, isn't it? Any system or component you can see, it can have a number of states depending on its input and time. For example, you can see bank account. It is an object. So what it can what assume the states? When you are going to open a bank account, then it is in initial state, or you are just opening an account, open state or create state. Then when you deposit 1,000 rupees at the minimum balance, then it is the initial state. Then once the initial state, you can make any number of deposits or you can make any number of withdrawals. So then that is, you can say that working state. And if you are not operating your bank account for 1 year or 2 years or so, then it becomes which state? It achieves dead states or idle state. And when you again take permission from the bank manager also, again they activate. So again it will come back to the working state. And when you completely close this account, withdraw all the amount and close the account, then it becomes what? Closed state. Okay. So in this way, we have seen that any system or a component, it can have many states depending on its input and the time. A system or its components may have a number of states depending on its input and time. And let's see in a state transition diagram how the states are represented. So the states are represented by the nodes. Okay. So the different states, they are represented by nodes. So these nodes you can draw as the rectangles or even if what rectangles with rounded corners also. With the help of nodes and the transition links between the nodes, a state transition diagram or a state transition graph can be prepared. So with the help of the different nodes and the transitions or and the transition links between the nodes, a state transition diagram or the state graph can be prepared. So now let's see a few of the important things on state graph. A state graph is the pictorial representation of an FSM. Okay, when you discuss a state graph, it is the we can say that already you have known FSM earlier. I will not discuss on FSM. So when you say that a state graph, it is the pictorial representation of an finite state machine. What is its purpose? What is the purpose of the state graph or state transition diagram? Its purpose is to depict the different states that a system or its components can assume. So a state or a component, it can assume, a system or a state can assume what different states that can be depicted, that can be represented by a state graph. It also shows the events or the circumstances that cause or result from a change from one state to another. So when a transition takes place, okay, when a state changes from one state to another, due to what events? Because only when some event will occur, the state may be changed from one state to another state. So when some events will occur, then the state of a system may change from one state to another state. So this state graph will represent those events. Okay, it shows those events or the circumstances that cause or result from a change from one state to another state. So state graph also represents those events. Whatever is being modeled is subject to inputs. So please remember that whatever you are modeling, what system you are modeling, what characteristics you are modeling, whatever is being modeled is subjected to some inputs. As a result of these inputs, when one state is changed to another, it's called a transition. That you know what is what event, what is a transition in FSM you have already studied. So I have told that whatever you are going to model, it is subject to inputs. As a result of these inputs, when one state it is modified, it is changed from one state to another state, it's called a transition that you have already studied in FSM. How do you represent the transitions in a state graph? The transitions are represented by links that join the nodes. Nodes represent what? I have already told you. Nodes represent states. So states are represented by nodes, and the links between the nodes, they are called as transitions. So transitions are represented by links that join the nodes. Now let us explain this state transition diagram or the state graph by taking a suitable example. So let us take an operating system example. I hope you must have studied operating system. So for example, a task in an operating system can have different states. What states it can have? So for example, a task in an operating system can have its following states. This task, initially it will be new state. That means when this task it is newly created, we call it state as new state. Then next state is ready state. When the task is waiting in the ready queue for its run, you know that when a task is arriving directly, it cannot be considered for running. It has to first enter into ready queue. So when the task is waiting in the ready queue for its turn to come, then we say that it is in a ready state. Running state, that means the working state. When the instruction of the tasks are being executed by the CPU, we call that the task is in the running state. And waiting state, when the task is waiting for any IO event or for reception of a signal, the task is waiting, we call that the task is in waiting state. And finally, when the task has finished its execution, then we say that the task has entered to the terminated state. So now let us draw the state transition diagram for this. I have already told you the states will be represented as nodes, and the links between them, they will be treated as the transition. So how many states I have identified here? 5 states. So let us draw those 5 states, and which transition will occur between 2 states. Now let's draw those things. Very simple. Please try to understand. What I have already told you, first state is new. So new is a state. I have told you that state I am representing as a node, either a circle or ellipse or rectangle, whatever you take. Normally people use ellipse. So new is the first state. So then what will happen from new, where it will go? Once a task is newly created, it has to go to the ready queue. And when this transition will occur, then we say that the task is transferred. It is what it has changed state from new state to ready state. That's right. New, and what is the event is technique? It is admitted. Admitted to who? What? Admitted to the ready queue. Then we say that the state is changed from new state to ready state. Then after the when the task is entering into the ready queue, when its turn will come, where it will go? It will start running. So that means what is the event occurs? Dispatched. When the task is dispatched from the ready queue, then it will be entering into the CPU for running or executing. So dispatch is the event. Then during running, many things might happen. If all your works are successfully over, then the task will be exiting from the CPU, and we say that it will enter into the terminated event. When this task is waiting for some IO or some event, then we can say that the task is it is changing a state from running state to waiting state. It also might happen a task might be interrupted due to some reasons. Then we say that the task will be changing its state from running to ready state. And you know, from waiting from ready state, it can go to only running state, nowhere from other state. So if a task is waiting for some IO or some event, and when that IO arrives or that event arrives, it cannot directly go to running state. Where it will go? Again, it will go to the ready queue. Again, it has to come till its turn comes. Then only when it will be dispatched and it will come to the running state. So in this way, I have simply drawn a state transition diagram or a state graph for a task in an operating system. And these states I have already told you. What is new state, what is ready state, I have already explained. So this is this graph. This is the state graph for the tasks in an operating system. Now let's say each arrow, you can see arrows, they represent what? The transitions. When some transition will occur, the object or this task will change its state from one state to another state. So each arrow link provides two types of information. So each arrow provides two types of information. Number one, the transition events. First one is what? First information represents the transition event. For example, admitted, dispatch, interrupt, IO or event, exit, IO or event completion. Those things are all examples of what? These are all examples of what? Transition events. Then what is the other information? Two types of information this each arrow represents. One is the transition information, another is the what? Another is this. We'll see. Number two is the resulting output from a state. What are the results? Those are obtained from the output, like new the state. So what result is obtained from the what resulting output? What is the resulting output from a state new? So we say that output we can say T1. From ready, what is the output? T2. From running, what is the output? T6, like this. So each arrow link provides two types of information. Number one is the transition events like admitted, dispatch, exit, or event wait, or event completion, interrupts, etc. And number two is the resulting output from where? From a state, just like as T1, T2, T3. So T1, T2, T3, T4, T5, T6. These are the resulting output from the different states. What is T0? T0, you can say that the task is in new state. It is in just new state and waiting for admission to the ready queue. So here I have not shown that means before new. It is just in what we can say it in new state and waiting for admission to the ready queue. But what is T1? A new task admitted to the ready queue. So after new, what is coming output? T1. So what is T1? T1 is a new task admitted to what? Admitted to T1. So here new is there. So some echo. Hello. Okay. So this new from the new state, when the transition happens admitted, what output we are getting? T1. What is T2? What does T1 represent? It is a new task which is admitted to the ready queue. After ready queue, when the dispatch event occurs, what is the output? T2. T2 represents what? It is a ready task that has start running, because after ready queue, when it's so when it is in ready queue, when its storm will come, then it will be dispatched and it will start running. So T2 will represent a ready task which has started running. What is T3? See, T3 is from running to ready. That means, and when some interrupt occurs, then this a task which is running that will be interrupted and it will again send back to the ready queue. So T3 only represents the output of running state. So T3 says that it represents a running task that has been interrupted due to some reason. What is T4? Again, T4 means from running it is coming to the what? It is coming to the waiting. And what does it mean? T4 means a running task. It is waiting for an IO event to occur. IO or event to occur. What is T5? T5 means the IO has already arrived or the event has arrived. So now again it will be ready to go to the ready queue. So T5 means the wait period of the waiting task is over, and now it will be again sent to the ready queue. What is T5 we have seen. What is T6? T6 is this. That means a running task. It has completed its job. Now it will be terminated. So T6 represents the output, which says that the task has completed execution and hence it will go to the terminated state. Very simple example I have taken, that is for this task in an operating system. So this is what? This is the state transition diagram or the state graph for this example. Which example? That operating system. It acts in an operating system example. Next definition is what? State table. So what is a state table? As its name shows, it is a table where some rows and columns will be there. But let's see what does the rows represent, what does the columns represent. So each row of the table corresponds to a state. So there, that means they represent what? They represent each rows of the table correspond to a state. So here what are the states you can see? New, for new we have created a row. Then ready, next ready we have also created next row. Then running, we have created a row for running. Then waiting, we have also created a row for waiting. But we have not created the terminated. This is the end state, last state. For that, no row is required, no state required, because the final state or the ending state. So that's why no row has been added in this table. Then what do you mean by column? Each column corresponds to an input condition. So each column corresponds to what? An input condition. And here what are the input conditions? The events. So what is the first event? Admit. What is the second event? Like this, dispatch, interrupt, IO or event completion, exit, IO or event wait. These are all what? Conditions or the events. They will be represented as what? Column. So I have written how many transitions are there? Admitted 1, dispatch 2, exit 3, IO or event 4, interrupt 5, IO or event 6. Conditions there are 6 events are there. So hence I have to draw 6 columns. 1, 2, 3, 4, 5, 6. For the 6 conditions, for the 6 events, I have drawn 6 columns. Now how to fill the entry? Just see, very simple. So the meaning is like this: when the state is a new state and the event admit occurs, what output you are getting? That means what will the new state and what will the output. Refer to the figure. When it was in new state, event has occurred, admit.
Not changing.
Yes.
The slide is not changing.
Sorry?
Just diagrams page.
Okay, now it is changing or not? It's changing or not changing?
So
Any other person?
No, sir, not changing.
Not changing. No? So now they are in which diagram? Now you are in which diagram is visible to you?
You are in the
State
correct
graph.
page, sir. You are in the correct page. It is new ready old diagram that is there. You are explaining that.
A diagram only.
Yes, yes.
So I'm just. Now see that table is looking. State table is looking. State table. Just check again. Hello. Hello.
no, sir, there is no table.
No, sir. It's a diagram only.
We are
No,
diagram, sir.
Okay, let's see why it has happened. Then otherwise I have to share again. Let's see.
Sir, you can reshare again. It will work.
Well, let's share again. So now is it visible? Hello?
Yes, yes. It is visible. The table we can see.
Yes, sir. Now it is visible, sir.
Okay. So what I was saying, that from this state transition diagram or the state graph, how you can construct the state table? Because once the state table is constructed, it is easy to design the test cases. So first step is construct the FSM, and then from the FSM you can construct the state transition diagram or the state graph. From the state graph, then you try to construct the state table. So now this is my state transition diagram. I am constructing a table. How you can in some rows and columns. The rows will represent what? I have already told you. The rows will represent the states. What the columns will represent? The columns will represent the what input condition or the events. So what are the states here? You can see there are 5, 1, 2, 3, 4, 5 states. So normally for the last stage or the terminated state, no need to construct a row. So that's why I have not constructed a row for that. Another 4 I have constructed. How many events are there? You can see there are 6 events. So I have constructed 6 columns. Now let's see how you can fill the cells. How you can fill the entries in the cells. Now let's see. Event the state is new, event is admit. Let's see. State is new. What event has occurred? Admitted. So we have to write down what? This what is the output? Let me check again. What the intermediate states? What the intersections they represent? The box are the intersection of a row and a column specifies the next state and the outputs, if any. Please remember, the rows will represent the states, columns will represent the conditions or the what you can say the transitions and or the events you can say, and what this intersection of the cells will represent. The box are the intersection of a row and a column. It will specify what? It will specify the next state or the transition and the outputs, if any. So what is the next state and what will the output, if any? That will be represented by this intersection. So let's see. First one, from new. When you are applying admitted operation, admitted event, what will the next state? You can see next state is ready, isn't it? And what will the output? T1 will be the output. So that I have written here. See, when the new state is there, you have applied admit event. Then what is the next state? Ready. And what is the output? T1. You can see from ready, from new reach at ready. All other states are not reachable. So what now you have to write? Then now how you can write the other states? Like new to dispatch, no state change, isn't it? Just say if you are applying new, you are in new state and dispatch. It is not dispatch, it's performed on ready state. So new and new with dispatch means no state change, because I cannot apply dispatch on new. So only in new state I can apply admit event, and the output will be next state ready, and the output is T1. That's why I have written T1 is the output. All other events cannot be applied. So if they cannot be applied means there is no state change. Same state new will remain, no state. So that's why I have written new, and T0 means the what tax was in the there. But T0 that the tax is in new state and waiting for admission to the ready queue. So similarly, you can see ready, and from ready you can go only to running state. The next state will be running state. By applying which event? Dispatch event. You cannot apply any other event in ready state. So ready to running will happen only when there is a dispatch. All other things, no state change. That means same will be there. So that's what I have done. Ready, when state is ready and event is what? Dispatch, then only you can go to running state. Please see. Ready, when you have applied dispatch, the next state is running state. And what will the output? T2 will be the output. So that I have written here, running and T2. All others, no change. So that means no state change, because I cannot apply. Ready to admit cannot apply. See, admit is from new to ready. From ready I cannot apply admit. So all other, so since I cannot apply admit on ready state, that means no state change. Ready, and the same what output? T1. So all other things, all other events cannot be applied. So no state change. So ready, and output is T1. But now let's say running state where we can go. From running, I can go to 3 states. If you are in running state and your event is exit, you can go to next state is terminate. If current state is running, event is IO or event wait, the next state will be waiting and output will T4. If the current state is running and event is interrupt, then the next state will be what? Ready state and output will T3. So there can be 3 new states you can arrive from running state. I have written that thing. From running, when you apply interrupt, you will go to ready state. You can see running interrupt. Running is the state, interrupt the event, you will go to ready state. From running, if you exited the event you have applied, you will go to terminate state. From running, if you apply the IO or event wait, then you will be moving to the next state, will be waiting state, and output will be T4. That's how it is. So running and you have applied interrupt, next step is ready and output T3. In running state, if you have applied IO or event wait, again it will go to waiting state and output will be T4. And from running, if you will apply exit state, your job is completed. The new state will be terminated, output will be T6. All other states will be no state change. So running, output will be 72. And from next waiting, from waiting where you can go, you can see only from waiting you can go to ready state when the event IO or event completion occurs. All others, no state change. So that's what I have done. From waiting, only when IO or event wait is over, then only a state change will be there, that is ready, and output will T5. What is T1, T4, T5? I have already described here. And now, from waiting, I can go to only ready state only when IO or event wait is over, and all other times, if you will apply all other events, they cannot be applied, so there is no state change. So in this way, I can construct the state table from the state transition diagram or the state graph. Okay. Now let's quickly look at the state table based testing. How can generate how can generate test cases from state table based state tables. So now we have finished the basic concepts, the important definitions that we require. After reviewing the basic concepts, now you can start functional testing with or by using state tables. What are the what are the different steps? Now, first step is identify the states. So, first step is identify the states. Then how to identify? The number of states in a state graph is the number of states we choose to recognize or model. How many states you are given? The number of states in a state graph will be the number of states we choose to recognize or we want to model. For this, we have identified that the task can be what new running, waiting, terminated. Like this, we have identified that this could be the possible states a task can migrate or a task can move from one state to another state. So these are the different states. Accordingly, you identify the states. The other example I have given account. For account, what are the possible states? New or create. Next is the initial state. Next state is running or working state. Next state is the idle state if you are not working for so many days. And next is what? Next is closed or dead state when you completely withdraw your money. So these are the states for account. States. The first step, what in design test cases state. So first step is number of states we choose to recognize the model. So how to finding out number of states? There, but some guidelines are there in your book. So a state can have what are the different component factors? First, identify all the component factors of the state. Identify all the allowable values for each factor. Each factor can assume how many values. Like say, suppose a ball you are taking, a switch. So its state now you can say that it is one status you can take. That is a state. The status can take either two values, either it is on or this is off. So identify all
Hello,
the
sir.
allowable values for yes.
Hello, sir. I think slides are not changing, sir. I am still at state graph, sir.
Yes, sir. Same
It's
here.
not
Yes, sir. It is the same.
Yes, sir.
So yes.
okay. Just wait. Let's see. There's some problem. So now this state now it's visible. Yes. Hello.
Yes, sir. It's
Yes,
not
sir.
stable.
Yes, sir.
State table based testing.
Yeah,
Yeah.
it is correct. Straight
So I am repeating again quickly the different steps. First step is identify the states. That means you have to say that what could be the possible states. The example of these tags, different states I have given, the different states of an account object I have given. So first step is identify the states. So first step is to identify the states. The number of states in a state graph is the number of states that we choose to recognize or we want to model. The full number of states. There is no such strict guidelines or strict formula for the number. The guidelines are given in your book. You can look at them. First, identify all the component factors of the state. So component factors of the first you have to identify all the component factors of the state. How many component factors are there that you have to identify? Then identify all the allowable values for each factor. For each factor, what are the different allowable values that you have to see?
Hello, sir.
For example, yes.
Sir, I think it is
Yes.
again on the state table based testing, sir. Step 1, identify the state, sir. I'm only seeing that. State table based testing. I'm on that one. I think you have changed the slide, but I cannot see it, sir.
Some problem.
Moreover, sir, your voice is also dropping a lot, but I mean, PPTs.
Now it is showing state table based testing. Hello.
Yes, sir. Step 1 it is showing, sir. Identify the states.
So first step I have already told you. First step is to identify the states. Here the number of states in a state graph. We have to identify the number of states in a state graph is the number of states that we want to choose or to recognize or to model. Okay, so the number of states in a state graph, the number of states we choose to recognize or we want to model. Now there is a slide change. Finding the number of states, is it visible?
No, sir.
Finding the number of
No, sir.
states.
No, sir. No, sir.
Difficult. That means in which slide now, which slide is visible to you? Which slide?
So step 1, sir. Identify the states. Still we are on that slide.
Some problem, I do not know. Some. Just do one thing. Let us. Camera is already off. So each time then. Now this step 2 is visible. Hello. Is step 2 visible? Anyone
No,
please?
sir.
Is
No,
step
sir.
2 visible?
No, sir.
Now
No,
which
sir.
step?
Step 1, sir.
No, it's voice is going, audio is going, but I don't know what to do. So just 1 second, let's see. So now what slide is visible? Yes, please. What is the slide visible now?
Slide number 1.
Huh. So that means now let's see. Now step 2 is visible.
Yes.
Yes.
Yes, sir.
Okay. So just let's quickly finish up. So step 1 I have already told you. Here first we have to identify the states, and the number of states in a state graph is the number of states we choose to recognize your model. As I have told that there are no such clear cut formally how to know the number of states, but some guidelines are there. You can see. We have to first do the following. First identify all the component factors of the state. Then identify all the allowable values for each factor. Suppose you have taken a bulb or light or switch. There can be maybe a state like a status. That switch can take 2 values like on or off. But identify all the allowable values for each factor. The number of states is how you will find out the number of states. The number of states is the product of the number of allowable values of all the factors. So how many factors you have identified? That means how many component factors. Each component factor can take how many values. So the number of states will be equal to the product of the number of allowable values for all the factors. This is another one guideline is there. Similarly, just look at the books for the guidelines. I will take this example and let us complete how to find out the test cases. So first identify all the component factors of the state, then identify all the allowable values for each factor, then the number of states will be, it is the product of the number of allowable values of all the factors. Now step 2 is what? Prepare the state transition diagram. After understanding the transitions between states, I have already taken the example of these tags, how to in the tags in operating system, how you can prepare the state transition diagram for a tags in operating system. I have already explained. After having all the states, we have to identify the inputs on each state and the transitions between the states and prepare the state graph. Okay. So first, identify what are the states. After having all the states, then we have to identify the inputs on each state and the transitions between the states, and then we have to prepare the state graph. How to prepare the state graph, I have already shown through an example. Every input state combination must have a specified transition. Okay, so for every input state combination, there must have a specified transition that you can also state that also you can see in the previous example. Step 3, 4 are easy. Step 3 is convert the state graph into the state table. as discussed earlier. I have already shown you how we can construct a state table from a state graph. Convert the state graph into the state table as discussed earlier. Then you can analyze the state table for its completeness, whether the state table is complete or not. That you have to verify. For example, I have seen in my previous example how many in that state table. I have seen there are actually 5 states, but one is the ending state I have not considered. So 4 states, and how many what conditions or events? 6. 6 into 4 means 24. So there must be 24 entries here. Then only that state table is complete. You verify that, you check that whether your state table is complete or not. That's what I'm saying. Analyze the state table for its completeness. Next is step 5. Step 5 they says that develop the test cases from the state table. How? In a tabular form with the following entries. In that table, these following columns should be there. First column should be the test case ID. Every test case must have a unique ID. A unique identifier for each test case must be given. Then test source. Test source means a trace back to the corresponding cell in the state table. So in the whatever I will show an example, in that tabular form, you can easily trace back to the cell in the corresponding state table because we have already drawn the state table before this. Then you know that the current state you have to show. What is the current state? What is the next state? So current state is what? The initial condition to run the test. Okay, what is the initial condition? What is the initial event that will be required to run the test? That is the current state. What is the event? There must be another column for the event. The input triggered by the user. Okay, what input is triggered by the user? That is the input. And output. Obviously, test case means the input and the expected output. So output is the current value returned. What value is returned currently? Next state is what is the next state? The new state achieved. So these columns must be there. Now let us quickly look at the complete test case. I have taken the same example, operating system example. I hope the larger table is visible to you now. So as I have already told you, what is the first column? Test case ID. So I have prepared the first one, test case ID. Then what is test source? Test source means it must correspond to the cell in the state table. I will tell. So from which cell in the state table I have got that the corresponding test source. Then I have already told you test case means I have to write down the input and the expected output. What will the input here? Input is the current state. From which current state we are getting the next state, and based on what event, based on what transition. So here input means 2 things: the current state and the event or the transition takes place. What are the outputs here? What will the next state and what will the output from a state? So output and next state. Now I am explaining 1 or 2 rows. You can try to understand others. So first I have taken TC1, test case 1. And for this I require the state table. Where is my state table? I hope now you are able to see the state table. So in the state table, see first, this is the first cell, first entry, new, isn't it? First state is new. And for new, what is this what? See, there must be 24 things you can see. There are 4 states, 6 events. So 24 entries are there. 1, 2, 3, 4, 5, 6. I can name this one. Ready T1 is the first cell. New T0 is second cell. New T0 is here the 6th one. 7th one will be ready T1. And like this. 14th one is ready T1. Like this. I can number them as 1, 2, 3, 4 like this. So that I can easily identify, mark them in my table. So what I am doing here, explaining the first one. TC1 is the first test case ID. Where I have got this one, test cell number 1. What is the cell number 1? Cell number 1 is the ready and T1. Okay, so that means the input consists of 2 things. What is the current state? So current state I have to say this is cell number 1. What is the input for this? Input is what is this current cell, current state, and what is the event. How I got that ready? When the current state is new the event applied is admit, or the the transition is admit, then I go to ready. So that I have explained here, new and admit, then I am reaching at ready state with output T1. So again I am explaining. Test case ID TC1, the test source from the state table is cell 1. What is the current state? The current state was new. What event has applied? Admit. And what should be the expected result? If you are in new state, applied admit, the next state must be ready and output T1. So that's why I have written this. You can see at the figure, new this state, you have applied admitted. So output will be next state ready and output T1. That I have shown here. See, L1 is the my test source, current state is new, event is admit. What should be expected results? Expected result should be the next state is ready state and output is T1. Similarly, let's go to cell 2. Cell 2 is which one? This one, new T0. So for this, what is the current state? Again, new. What is the output? What is the event? Dispatch. So these two are the inputs, new and dispatch. What should the output? New and T0. New will be, next state will be new, that means no state change, and output is T0. That's it. This is cell number 2. So for cell number 2, what is the current state? It is new. What is the event has occurred? Dispatch. And what should the expected output? No state change. So that's why new state also new, and output is T0. Like this, for how many test cases will be there? I have already told you, 4, 6 events. So 4 into 6, 4. So 20, and accordingly you can easily write down the test cases. So basically what we are writing here, the inputs and the expected outputs. And in order to map, in order to trace back to the state table, we are writing this test source. So there are 24 cells, so 24 number of cells are here. So any doubt, please? This is how we can design the test cases for this. For this, tax example in operating system using what? Using state table based testing or using state tables. Any doubt, please? Yes. Please have a look, and any doubt, please just ask me. Not possible today, you read it today, and maybe the next class you can ask me. It's a very simple thing, but one full question may come from here. If you understand, basically 3 important things. First, construct the state transition diagram or the state graph. Then from the state graph, construct the state table, and from the state table, how many cells are there? So many number of test cases you have to design by preparing these columns. One is test case ID, then the test source with respect to the state table, then the input and expected outputs. Input will represent the current state and the event or the transition that you are applying, and the expected output should be the next state that you will reach from the current state, and if any output is there. In this way, you can design the test cases using state tables. Yes, any doubt, please? No. So there are no more doubts. See, so what is the next class, MTech students? Anyone? BTech students? Puranand, is it audible or not? Hello?
Yes, sir. You are audible, but for PhD we have I think NLP classes there, 11 to 12.
Yes, sir. We also have NLP class.
Okay. Okay. So let's stop, and next class we'll meet. Okay. So please have a look. It's a very easy thing. And if you have any doubt, please ask me in the next class. Thank you very much. You can leave now.
Thank you, sir.